Hello everyone. In the previous lecture, we have defined isomorphic graphs and we have proved some necessary conditions for two graphs to be isomorphic. But still we need a sufficient condition for the isomorphism for two graphs. Firstly, we introduce some more basic concepts. So let us take G, which is BVE. This is a journal graph. And now we take a sequence of m edges. Now the sequence is given by x0, x1, x1, x2, up to xm minus 1, xm. So these are m different edges and we have a sequence of m edges. Now this will be called a walk of length m, and this walk basically joins the vertices x0 and xm. This is walk of length m joining the vertices x0 and xm. And we denote this walk by this thing also, x0 to x1 to x2 and so on up to xm. We denote it like this. Now this walk is closed or open if x0 is equal to xm or x0 is not equal to xm. So we will say if its starting point is not equal to end point, then the walk will be called open, and if they are equal, then the walk will be called closed. Now in this walk we have used m different edges, but this walk may have repeated edges. But if walk has distinct edges, then it is called a trail. If walk has all the edges distinct, then it is called a trail. Now in addition, if a walk has distinct vertices except possibly for the first and the last vertex, and then it will be called a path. Now if walk has distinct vertices, obviously if it has distinct vertices, then it has distinct edges also, then it will be called a path. And closed path is called a cycle. Now we can easily check that the edges of a trail. Now trail is a walk which has distinct edges. Now edges of a trail joining the points x0 and xm, they can be partitioned so that one part of the partition determines a path joining x0 and xm, and the other part determines cycles. Because here we are saying that it has distinct edges, but it may have distinct vertices. So we will partition in this trail in such a way that we get a path we get a path joining x0 and xm, and the other parts which are remaining parts, and they determine cycles. The edges of closed trail can be partitioned into cycles, we can say. The length of the cycle of graph is at least 3. Because whenever we have an edge, it goes from one vertex to another, and for a cycle, end point and starting point, they must be same. So for a cycle of graph, the length is at least 3 because it contains at least 3 vertices. three edges, sorry. In a general graph, if we have a loop means a closed edge, an edge from x to x itself, that will be called a loop. So a loop is a cycle of length 1, and we have a, and if we have edge AB, which is of multiplicity 2, which means there are more than two, yeah, there are two or more than two edges from the point A to B, then that also determines the cycle. And that cycle is like that: A to B, then B to A, and that is having a length 2. So whenever we do not have a loop and we do not have a edge of multiplicity more than 1, then we can say that cycle has length at least 3. So now we consider this example. Let us say this is the graph. So we have one vertex here, that is D, and three vertices like this. This is A, B, and C. One more vertex E is here, and we have F, to which there are three edges from E, and one loop from F to F itself. And we have H here. Again, we have three vertices, three edges from G to H, and one loop from G to G. And let us take, we have a point M, and this is vertex K, edge from K to M, edge from I to K, and two edges from K to L, and two edges from K to J. So let us say this is the graph. This graph has 13 vertices, and in this graph we can easily see that if we take this A, D, then B, D, C, D, H, G, H, M, K, I, then this is a walk. Now we go from A to D, then D to B, then further B to D, then D to C, C to D, then D to H, H to G, G to H, H to M, like this, and M to K, then K to I. So this is a walk of length 11. Now because this walk contains edges more than once, this edge BD more than once, this edge CD more than once. So this is not a trail, because trail is that walk which has distinct edges. So this is a walk of length 11 because it contains 11 edges. From A to I, but it is not a trail. Number one. Secondly, if we take A to D to E to F to E to M, K, L, K, I. Now this is A to D to E to F to E, then to M, like this, then to K, then to L, then again K, then I. Now this walk, this contains distinct edges. So this is a trail. So this is a trail of length 9, and this is a trail from point A to I, but it is not a path because it contains the point E twice, because the path is a trail which has distinct vertices. So this is a trail but not a path. Now we define this A, D, E, M, K, I. Then this will be a path A to D, D to E, E to M, M to K, then to I. So this walk contains distinct edges as well as distinct vertices. So this is a path of length 5 joining A to I. Then further, if we take this D to E to F to E to M, H, D. Now this is a closed trail because it starts from D and ends at D. So this is closed trail, but it is not a cycle because cycle is basically a closed path, and this contains the vertex E twice, so it is not a path. So this is a closed trail, but not a cycle. And if we take F to F, this loop F to F, this loop G to G, then F to F, G to G, and if we take E to F to E, now we have this E to F along this edge and F to E along this edge. Now this has and starting and end points are same, and it contains different edges, so it is a cycle. Then D, E, M, H, D. So this is D to E, D to E, then M, then H, then D. So this is also a cycle. So all these are examples of cycles. Now we define connected graph. A graph G is called connected if for each pair of vertices X and Y, there is a walk joining X and Y. So if between any 2 points, there is a walk joining X and Y, then we say the graph is connected. Otherwise, the graph will be called disconnected. That means in a disconnected graph, there is at least one pair of vertices X and Y such that there is no walk from X to Y. So now we define dxy for a connected graph G. We define dxy. Dxy is the shortest length of a walk joining X and Y. So we take all the walks joining X and Y and we take the walk of shortest length. So this dxy is that shortest length, and it is called the distance between between X and Y. So this is called distance between X and Y. So if we take dxx, then this is the shortest distance between X and X, and that will be always 0. So we take dxx to be 0 for each vertex X. Now obviously we can say if we have a walk joining X and Y and its length is equal to dxy, then it will be a path because dxy, this is the shortest distance between X and Y. That means the edges, they are not repeated in this dxy. So it means the walk and joining X and Y with length dxy, that is basically a path. So it will not contain repeated vertices and will not contain repeated edges. So for example, we can draw this graph. This graph has 7 vertices. Let us say these are the 7 vertices A, B, C, D, E, F, G. Now in this graph, there is no walk from the vertex B to vertex G. So it is disconnected graph. Because there is no walk from this to this vertex, similarly C to D, C to G, and so on. Now we define subgraph. So let us take G is VE and this is a general graph. Now we take U to be subset of V and F is subset of E such that vertices of each edge in F belong to U. Now because F is a subset of E, so F is also collection of edges. But we are taking F to be that subset of E such that vertices of each edge in F that belong to U. Then the graph with set of vertices U and set of edges F, that is also a general graph, and this will be called subgraph of G. Now if F consists of all edges of G that join vertices in U, then it will be called induced general graph of G. If F contains all the edges of G joining the vertices in U, then it will be called, then G dash is called induced subgraph. And it will be denoted by GU. It is induced by the subset U. Now if we take U to be the entire set V of vertices, then G dash is called spanning subgraph. If U is equal to V, then G dash is called spanning subgraph. It means induced general subgraph of G is obtained by selecting some of the vertices of G and all the edges of G that join them. And a spanning general subgraph is obtained by taking all the vertices of G and some of the edges of G. So for the induced subgraph, we take subset U of vertices set V and we take all the edges which join the vertices which are in the set U. That will be induced subgraph. And for a spanning subgraph, we take all the vertices and we take some of the edges of G. So that will be spanning subgraph. And now again we take the example which we have drawn above. This example, this graph. Now in this graph, if we take only this much portion, now if we take this to be graph G and we take now this is our D, C, A, E, H, then this vertex is G, this is F. So if we take only this much portion of graph G, then it will be a subgraph which is neither induced nor spanning. For the induced subgraph, we have taken the vertices A, C, D, E, F, G, H. but we have not taken all the edges joining these. We have here 3 edges from E to F, but we have taken only one here, so it is not induced. And it is not spanning because it does not contain all the vertices. This is not spanning subgraph. Now we take only this much portion. Now this is vertex J, this is K, L, I, and M. This much portion. Now we are taking here J, I, J, K, L, M, these vertices, and we have taken all the edges joining J to K, I to K, K to L, K to M, and so on. All the edges joining in this. So this graph is basically induced graph, but it is not spanning because it is not containing all the vertices of the graph. Then we take this portion. Now this is D, A, B, C, H. Now this is G, K, L, I, J, M, and this is E, this is F. Now we take this subgraph. Now this subgraph contains all the vertices. So it is a spanning subgraph. It contains all the vertices but some of the edges. So it is spanning. But it is not induced because it does not contain all the edges joining the vertices in this set. So it is not induced. So this is how we can define induced subgraphs and spanning subgraphs. Now in this theorem, in the next theorem, we will prove that a general graph which consists of one or more connected general graphs, that is, that has some conditions which are satisfied by this graph. So we have this theorem. Now G, let us take G to be VE, which is a general graph. Then the vertex set V can be uniquely partitioned into non-empty parts. Then this V can be uniquely partitioned into sets V1, V2, Vk, such that these conditions are satisfied. Number one, if we take the general graphs G1, V1, E1, G2, V2, E2, and so on, GK, VK, EK, and if these are induced graphs by the vertices set V1, V2, Vk, the graphs induced by these sets are all connected. Then secondly, for each I not equal to j and each pair of vertices, say x in Vi and y in Vj, there is no walk joining x and y. For example, here in this graph, now in this graph we have 7 vertices, and we can partition this graph into 2 different graphs. One is graph this, which contains these 3 edges and the 3 points ABC, and other is this graph which contains 4 vertices D, E, F, G and these 4 edges. So these two are induced graphs, So we can partition the set V into two induced subgraphs such that both are connected. So this triangle is connected, this rectangle is connected, but every point, if we take one point in this first graph and second point in the other graph, then there is no walk joining those 2 points. So if we have any general graph, then that can be partitioned like this. Now, in this partition, all these graphs G1, G2, Gk, these are called connected components of G. This G1, G2, Gk, these are called connected components of G. So part 1 of this theorem says that the connected components are actually connected sets, connected graphs, sorry. And part 2 says that the connected components are the maximal connected induced general graphs, which means if we take a point in Gi and if we take a point in Gj, then there is no walk joining x and y, means there is no connection between Gi and Gj for different I and j. So components are basically maximal connected induced general subgraphs. So we can define connected components like that. The connected components of a graph, they are maximal connected induced subgraphs. So now we can collect all the necessary conditions for the graphs to be isomorphic. Now if we have two different graphs, G and G dash, then the following are necessary conditions for these graphs to be isomorphic. Some of the necessary conditions we have done in the previous video. So if two graphs are isomorphic, then firstly, if G is a graph, then so is G dash. Secondly, if G is connected, so is G dash. Moreover, they have same number of connected components. Then third one is if G has a cycle of length equal to K, then so does G dash. If G has induced general subgraph, that is a complete graph Km, then so does G dash. If G has an induced subgraph that is complete graph of order M, now we make adjacency matrix for the graphs. let us take G is a general graph of order n and its vertices are a1, a2, an. Then we define an n by n matrix A whose entries aij are given by number of edges joining ai and aj. So we have a graph G whose vertices are a1, a2, an. This is graph of order n. And then we define a matrix A, which is n by n matrix. And the entry aij will be given by number of edges joining the vertex ai to vertex aj. Or we can say aij equals 1 if and only if ai and aj have one edge between them. So let us take this graph and we will make the adjacency matrix of this corresponding to this graph. Now let us take, we have 6 vertices. Say this is A1, A2, A3, A4, A5, A6. Now we have a loop from A2 to A2. We have 2 different edges from A2 to A5. One is this, another is this. Then we have an edge from A1 to A5. Now there are 2 edges from this to this. Here we have 2 edges, one edge from A3 to A4, then 2 edges from A4 to A5, then a loop from A4 to A4. So let us take this graph and we will make the adjacency matrix. Now it has 6 elements, 6 vertices in this graph, so the matrix will be 6 by 6 matrix. Now the first entry of the matrix will be A11, which means number of edges from A1 to itself, but there is no edge from A1 to itself. The next entry is A12. Between A1 and A2 there is only one edge, so the entry will be 1. A13, A1 and A3 there are 2 different edges, so this is 2. A14, there is no edge from A1 to A4, so this is 0. A1 to A5, there is only one edge. Then A1 to A6, there is no edge, so it is 0. Then from A2 to A1, this is 1. A2 to A2, we have one loop, so this will be 1. A2 to A3, no edge. A2 to A4, again no edge. A2 to A5, 2 edges. A2 to A6, no edge. And continuing this, we will get the matrix to be like this: 0, 0, 1, 1, 2, 2. Then 1, 2, 1, 2, 0, 0. Then it is 0, 0, 1, 2, 0, 0. So in this matrix, we can easily check that aij, that is equal to aji, because number of edges from ai to aj, that is equal to number of edges from aj to ai. So this adjacency matrix, that is uniquely determined by the graph, apart from the ordering of its rows and columns. This will be unique. But if we take this vertex to be the first vertex and this to be second, then third, then fourth, then fifth, then sixth, then corresponding to each vertex, it has one row in this matrix. And if we interchange the order of these vertices, then the order of rows in this matrix, that also will be interchanged. That means except from the ordering of rows and columns, this matrix is uniquely determined. And the sufficient condition for the graphs, for two graphs to be isomorphic to each other, that they have same adjacency matrix. If two graphs have same number of vertices and that means there is one correspondence theta between the vertices set, such that if whenever there is an edge from x to y, then there should be an edge from theta x to theta y. That means their adjacency matrix should be same. So we can now say that the sufficient condition for two graphs to be isomorphic, that their adjacency matrix is same. So G and G dash, the sufficient condition for G and G dash to be isomorphic is that their adjacency matrices are same.